afternoon, ladies and gentlemen. My name is Dr. Jon Belkowitz from Intelligent Concrete, and I am excited. I have the privilege of diving into the PMXDB number 16. We're going a little bit out of order here, folks. We've got this awesome project with the United States Air Force, part of which we're working with the United States Air Force Academy cadets. Howdy, y'all. And we're helping junior engineers learn how to do things like concrete mix design, structural design, pavement design, rigid pavement design, which Haley will be getting into later on. But today we're going to go into pavement design. So, yeah, this is what we're going to be getting into. We've got a job site coming up, late August, early September at the Air Force Academy. We're going to be working not only with Martin Marietta, Air Force Academy, specification products, and we're going to be using colloidal silica and concrete, but this is the basic mix design that we're starting out with. This is the benchmark. So excited to kick this off. Let's get into the math. Okay, so our parameters, what do we care about? We got a rigid pavement. Ultimately, we're going after a pavement that would be used on an airfield pavement, active runway or taxiway. Slump for 2 inches, whether we're doing a slip form paver. Might be a little bit less than that if we are going after a slip form paper or even a hand placement. We're looking at severe freeze-thaw rain as well as de-icing salts and brines. We use that here in Colorado. We want a compressive strength at 28 days of 6,500 PSI. Assuming this is a mix that we've never used before, we've got to add that 1,200 PSI for our factor of safety. So really want to shoot for a 28-day strength of 7,700 PSI, and then our design modulus of rupture is 650 PSI. I guess we could say the same thing, that we want to hit a factor of safety of that 120 PSI, so 770 PSI. Now, when we get into the ACI 211, what we use with the absolute volume method, you're going to see that we're not going to be able to shoot for this strength using the water cementitious ratios, but that's okay. We've got another method of using that, but I want you to use the lowest water cementitious ratio we can for that math, but we'll get into that here in a second. Our materials that we're using: crushed aggregate, absorption of 0.9%, moisture of 1.1%, specific gravity of 2.74, and a dry rotted unit weight of 97.2 pounds per cubic foot, and that's for our coarse ag. Our fine ag is a natural sand, fineness modulus of 2.73, so a bunch of fines in it. Specific gravity of 2.6, absorption of 1%. It's got a lot of moisture in it too. So let's start off with the math. Let's have some fun. All right, so as I go through the math, I'll update this over here, this table with all of our numbers, but I'll be erasing things just to keep it a little bit more clean and tidy. Okay, so if we go to table 6.3.1, recommended slumps for various types of construction, in it says we want, if we're making a pavement and slabs, we want a maximum of 1 inch, a maximum of 3 inch, a minimum of 1 inch. We've got our client specifying a 2 inch slump, so that's what we're going to stick with. Our first table, 6.3.1, our slump is going to equal 2 inches. Great. Now we go to our next table. This is where we're choosing our water. Now remember, we're working with a cubic yard worth of material here. We're going to section off a certain amount for each raw material. And the first thing that we handle is the water, and then from there we go to air. And that's going to be in table 6.3.3. So 3/4 inch ag, we are dealing with severe freezing and thawing, so we want to go to that lower section of table 6.3.3, the air entrained concrete, and with 3/4 inch with a 1 to 2 inch slump, we want 280 pounds per cubic yard. That's what that PCY stands for, pounds per cubic yard of our water. Now, outside of that, what we also get from that table, from that lower section, is the amount of air that we need in our concrete. And because we have severe freezing and thawing, or severe exposure, because we have a 3/4 inch ag, we're going to be at 6.0% air. There is a note on the bottom of table 6.3.3 that says if you have rounded rock, you can take a certain amount of that water out. We're using crushed rock. Can't take that water out, so we're sticking with 280 pounds. Now we're moving on. The next stage is determining our water cement ratio, and from there our cement content from our water cement ratio. We're going to start out with table 6.3.4a, and this is what I was referring to before about you only can go so low with your water cementitious ratio, and we're just going to use the lowest amount, which is 0.40. So our water cement ratio equals 0.40, and for those of you who don't know what water cement ratio means, it's weight of water over weight of cement equals 0.40. Before I run those numbers, we got to do one more check in table 6.3.4b. It's got this thing where you can't have a water cementitious ratio higher than 0.45 for a structure that is continuously wet. It's got all these checks in it, but we have a water cementitious ratio lower than these and a lower water cementitious ratio. Now, this goes back to Duff-Abrams law of 1918 and 1919, which was an empirical way for us to connect strength to the ratio of our water weight to our weight of cement. So with this, our table 6.3.4b, we're good to go. All right, so let's get into the math. So we're going to use a little reorganization here. We know our weight of water. This is our unknown here, so let's solve for our unknown. Our weight of cement equals, so this comes over, we've got our weight of water over 0.40. So our weight of cement, and remember, this is in pounds per cubic yard, equals 280 pounds per cubic yard divided by 0.40. Haley, help me out! 700? 700 pounds per cubic yard. So we're going to write that right up here, 700. How are we doing, Haley?
Great.
We got another measurement coming up?
We have 10 minutes.
Okay, Haley and I are working on ASTMC 403. So we've got to keep running out to do measurements. All right. So now that we've got that done, we need to start working on our coarse aggregate. We're going to jump over to table 6.3.6, and what we're going to find from that is we've got our information from our coarse and fine aggregate using our dry rotted unit weight and our fineness modulus. We're going to determine a ratio to use to give us a benchmark on the amount of coarse aggregate that we're using. Now, Haley asked a great question yesterday. Why are we using the fineness modulus of the sand to determine the amount of rock that we're going to use? Our fineness modulus is basically a measure of the amount of fines that we have in our sand. So if we're adding more fines, we want to kind of control or limit that surface area. So the finer the sand that we add, we want to pull back on our rock a little bit, and that's really what we're doing. So with us, we have, using table 6.3.6, we have a maximum size aggregate of 3/4 inch, thank you, Haley. Then we have a fineness modulus from our sand of a 2.73. And with that, I mean, you could do a linear extrapolation, but we're really going to be using that 0.63, which is that volume of coarse aggregate per unit volume of concrete. And we're doing that with different, how do they say, different fineness modulus of fine aggregate. So to do our coarse aggregate, and this is going to be in pound per cubic yard, it's going to equal that 0.63, and we're doing this in a 27 cubic foot per cubic yard basis, and we have to take into account our dry rotted unit weight, 97.2 pounds per cubic foot. And Haley, with that, how many pounds are we at? 1,653 pounds per cubic yard. Isn't that awesome? I absolutely love that portion. So 1,653. Now, if you wanted to, you could round that to 1,650. It'll make the math a little bit easier for you on paper, but quite honestly, once we get to the absorptions and the moistures it's going to screw it all up anyway, so you might as well leave it at 1653. So the next portion is we've got to figure out the sand content. Now we can do that one of two ways. We're working with an absolute volume. We've got 27 cubic feet in a cubic yard. So what we can do is determine the amount of cubic feet per material that we're playing with, and then from there pull out from 27 that total that we've already used, and that residual we can use with sand. Right? Another way of doing that is adding up all those materials, and then on table 6.3.7.1, there's something that's called the first estimate of weight of fresh concrete, and it's all based on aggregate size. So for a 3/4 inch maximum sized aggregate, they say your first estimate of fresh weight is 3,840 pounds per cubic yard. And I wanted to write that different because I just wanted you to see it out. Pounds per cubic yard. So if we start taking things out, Haley's going to work with me here. We take out 700 pounds per cubic yard, 280 pounds per cubic yard, 1,653 pounds per cubic yard. We're left with 1,207 pounds per cubic yard. I'm going to write that down in parentheses here because I don't like doing this method. This is my least favorite method because I don't know, as an engineer, I find it fun to run these story problems all the way through, look at the different specific gravities of the material, and actually play with the volumes. To me, it's more scientific. You don't have to do it that way. Remember, this is just a benchmark, so no matter what number we get here with this bookcrete, we've got to do the labcrete, we've got to work it out, and we've got to do that before we get to the plant level. You want to dial it in at a lower scale before you scale it up. Okay, so what we've got to do is, in lieu of using our estimate, we've got to determine our volumes for our individual materials. So we'll start out with our cement volume. We've got 700 pounds per cubic yard. The way we turn this into cubic feet per cubic yard is we divide our material by the unit weight of the material. Now it happens to be that the specific gravity of cement is 3.15. We multiply that by the unit weight of water, which is 62.4 pounds per cubic foot. So that equals 700 pounds per cubic yard divided by 196.6 pounds per cubic foot. Our pounds cancel out. We're left with 3.56. Okay, so the same thing for each one of these materials. I'm just going to go ahead and work through them. You do the math with me. Time lapse. No one can hear me singing time lapse. 'Cause I'm gonna do a time lapse. Time lapse. Okay, so now that we've got, the time lapse song. Now that we've got all of our values for materials that we've already looked at, now we've got to subtract 27 minus those volumes to see what we've got residual for the sand. So I'm just gonna go through here. Let's do another time lapse. Time lapse. So this is the volume that we have left over for our sand. Sand volume equals. So we'll go ahead and throw that in here. So let's go ahead and do the math. We're going to use the same information and the same method, but a little bit in reverse. We're going to determine the weight of sand, and we're going to do that by back calculating or using our volume that we have left over with our specific gravity. So we've got 7.66 cubic feet per cubic yard left over. We know that our specific gravity of our sand is 2.60. Our unit weight of water is 62.4 pounds per cubic foot. Our weight of sand equals 7.66 cubic feet per cubic yard. 162.2. We need 2 sig figs. Sorry to be a stickler here, but... So, weight of sand is then equal to 1,243 pounds per cubic yard. And we had 1,207 with our first estimate of fresh weight of concrete. And again, it's not my favorite method, so we're going to go back to our tried and true method using that absolute volume method. And that's 1,243. So, we've got all of our weights, but now what we need to do is adjust our design water, our design rock, and our design sand to take into account the absorption and the moistures that come along with the rock and sand. Now, when we look at a piece of rock, so we look at a rock, and obviously a rock does not look like a wonky soccer ball. But when you do look at a rock, if we put it under a microscope and made it look like a wonky soccer ball, there's a certain amount of cracks and pore spaces in our aggregate. Okay? And in a dry state, a bone dry state, this is what our aggregate is going to look like. In a saturated surface dry state, this is what our aggregate will look like. There'll be water within the pores, and we'll have something along the lines of, if our absorption is equal to 1%, our moisture will then equal 1% in this state. Now, if we have a certain amount of free water on our surface, or this free moisture, our moisture, while our absorption is still 1%, instead of our moisture being 1%, our moisture will be 4%. So we'll have a certain amount of free water on our aggregate that we need to take into account, because that free water will contribute to our water cement ratio. And of course, if we don't take that into account, we put too much water into our mix, one, we might not make the fresh properties, but two, we might not make the strength and durability that we're going after. Okay, so the weight of sand. Let's start with the weight of rock. So the weight of rock, and this is going to be adjusted, is going to equal our 1,653 pounds per cubic yard that we determined before, times our moisture plus 1. So 1 plus 1.1% gives us our weight of rock adjusted is 1,670 pounds per cubic yard. It looks like we have a little bit more work to do, and Haley! What? I lost my blue marker! Nope, I got my blue marker right here. We're good. So we've got our aggregate here, our sand. We need to take into account our moisture. We already did it for our rock. So let's do our weight, sand, and we'll call it adjusted. And just like before, we're going to take our original weight, our 1,243 pounds per cubic yard, and we're going to multiply it by our moisture plus 1 equals 1,243 pounds per cubic yard times 1.058, and that equals 1,315 pounds per cubic yard. And we'll go ahead and put that right here, 1,315, and we're good. This is going to stay the same. This is going to stay the same. This is going to stay the same. So we've got our updated coarse and fine aggregate. Now we've got to update our water. And what I mean by that is the water that we have on paper is our design water. It's our water that'll get us to our water cementitious ratio, water cement ratio in our case. Now what we need to determine is our batch water. And the difference between the batch water and the design water is that water that's coming from the aggregate, that moisture content. So the way we're going to determine our weight of water, and again this is adjusted, is going to be our 280 pounds per cubic yard minus, first thing we got to do is take into account our rock, which was 1,653 pounds per cubic yard, times our moisture minus our absorption. Then we're also going to subtract our sand, 1,243 pounds per cubic yard. So our new water is 217 pounds per cubic yard. I originally called it my weight of water adjusted. You can call it your batch water. And if we want to convert it to gallons, you divide your 217 by the conversion, which is 8.345 pounds per cubic yard, or pounds per gallon. 26 gallons per cubic yard. And let's go ahead and drop in our last 217 pounds per cubic yard, or 26 gallons even. We've got our mix design. We adjusted the waters. You know, the thing that we have to come back to is we need to be cognizant of our engineering properties that we need to go after. First and foremost, we had an original F prime is C, or 6,500 PSI. But when we look at ACI 318, I believe the newest edition is 2017. Anyway, there's a plus 1,200 PSI that we have to take into account. It might be a little bit more than that. Let's just say it's plus 1,200 PSI. Before you build your structure, please check the ACI 318 and make sure we've got those right numbers in there. So our assumption is that our F of R, our modulus of rupture, is going to be somewhere around 10%. Well, we originally started out with our modulus of rupture, and we were assuming that the flexural strength was only 10% of our compressive strength. So we need 7,700 PSI for our compressive. If we do the same thing with our flex, we need 770 PSI. Let's go ahead and clean that up and really try to identify what this means for our cement. What are we relying on? So we have a design strength that we need to achieve, let's say a maximum of 7,700 PSI. We know we have a cementitious weight of 700 pounds per cubic yard. So that means our KPI, our key performance indicator, which is in PSI per pound, right? Pound of cementitious. So if we do 7,700 over 700, and this is pound, excuse me, let me rewrite that, pound per cubic yard. We need a KPI of 11 PSI per pound of cementitious. You could say pound per cubic yard. But that's the efficiency that we need out of our cement to make this happen. Please bear in mind, there are cements that don't have an 11 PSI per pound. There are cements that only are hitting a 6 or 7 or an 8. But there are also cements that are hitting 12 and above. Now, we only need to hit an 11. Now, if our cement is only hitting a 9, there are things that we can do by adding either supplementary cementitious like silica fume, slag, Class F, Class C, fly ash. Then there are alternative supplementary cementitious materials you can use, colloidal silicas you can use, carbon nanotubes, titanium dioxide, nano alumina. There's so many different technologies that can help you boost your lower PSI per pound to that higher PSI per pound so you can achieve those engineering properties that you need without having to increase your cementitious content. Now, Haley, why don't we want to increase our cementitious content more than when we need to?
Because it's expensive and it's bad for the environment.
Right, it's expensive. How is it expensive?
It's the most expensive material in concrete.
It is the most expensive material in concrete with cost,
right.
But if you throw more water at concrete or at rock or sand, nothing really bad happens to it. If you throw more water at cement, you're going to tendency to create a very soupy mix, right? It's going to be soupier than what you originally started with. So the cement can be the most expensive component because it is one of the more difficult components to deal with in our concrete. So bear that in mind too. We want to use, God bless cement, I mean especially Portland cement, where it has gotten us in the last how many years is absolutely amazing compared to where we started with natural cements and using these other materials out there. But with cement, we want to be careful because we can also induce cracking. There are some things that we don't want out of it. So we want to use just as much as we have to. And if we can increase the efficiency and pull some of that powder back, as Haley said, not only to save the environment, to increase the durability of concrete, that's never a bad thing. And we're also going to see a value-added performance or a reduction in cost. As Haley said, that's one of our most expensive things in the concrete. So, yeah, that's the mixes that we ran through. That's a pavement mix. We're going to be working with Martin Marietta and probably getting a little bit more specific with their materials, what they've done in the plant, and how they dial it in. So we might not stick directly to this mix design, but you're going to see everything. Is there anything else I needed to cover?
I don't think so.
Really?
Stay tuned for the Stay tuned for the rest of the modules. There are 8, 9 that we are working through.
9.
So we'll get them out to you, and thanks for watching. Don't forget to like and subscribe. Ding that bell for notifications. Go Concrete!